Section: Introduction. In this section, we discuss long-context large language models, LLMs, that are built to handle longer input sequences, allowing for better understanding of extended contexts, such as the Gemini 1.5 Pro, which can process up to 2 million tokens. With enhanced computational capabilities, these models show improved performance in various tasks. For instance, many shot-in-context learning, ICL, can perform as well as supervised fine-tuning by using numerous examples. In knowledge-intensive tasks that utilize retrieval augmented generation, RAG, increasing the number or size of retrieved documents generally boosts performance, but focusing solely on the quantity of knowledge has its drawbacks. We note that current long-context LLMs struggle to effectively find relevant information in very long sequences, often not fully utilizing their maximum capacity. Additionally, retrieving too many documents can lead to performance plateaus or declines due to increased noise, which distracts from the task at hand. Therefore, scaling inference for long-context RAG remains a challenge. To address this, we explore various strategies to enhance RAG through improved inference computation. One approach we introduce is demonstration-based RAG, DRAG, where we provide multiple examples to help the model learn how to find relevant information and generate responses. However, the quality of retrieval can vary, prompting us to develop iterative demonstration-based RAG, ITER-DRAG. This method breaks down input queries into simpler parts and retrieves answers through interleaved steps, allowing the model to build reasoning chains for complex queries. We also investigate how to scale inference computation effectively. We measure this by the total number of input tokens used across all iterations, termed the effective context length. In DRAG, we can scale this by increasing the number of retrieved documents and in-context examples. In ITER-DRAG, we can further extend computation by adding more generation steps. Our goal is to understand how RAG performance relates to different scales and allocations of inference computation. Through extensive experiments on benchmark question-answering datasets, we find a nearly linear relationship between RAG performance and effective context length when combining both RAG strategies. Our methods outperform simply increasing the number of documents, achieving state-of-the-art results with the compact Gemini 1.5 Flash. We also identify inference scaling laws that show RAG performance improves with the effective context length under optimal conditions. We aim to model RAG performance concerning various inference configurations to predict the best parameters for maximizing performance across different tasks. By quantitatively modeling this relationship, we derive a computation allocation model for RAG that aligns well with our experimental findings and can be applied across different scenarios, optimizing the use of computational resources. In summary, we systematically explore inference scaling for long-context RAG, introducing two strategies, DRAG and ITER-DRAG, which effectively enhance inference computation. Our evaluations show that these methods not only achieve state-of-the-art performance but also scale better than merely increasing document quantity. We demonstrate that optimal allocation of test-time compute allows long-context RAG performance to scale almost linearly with increased computational budgets. Finally, we provide a computation allocation model that offers practical guidance for optimizing performance in long-context RAG tasks. Section Summary. In this section, we explore the scaling of inference computation for long-context retrieval augmented generation, RAG, using two strategies, DRAG and ITER-DRAG, which enhance performance by effectively utilizing long-context capabilities. Our experiments reveal that RAG performance improves almost linearly with optimal allocation of computational resources, and we develop a computation allocation model to guide the optimal configuration for various RAG tasks. Section: Related work. In this section, we discuss related work on long-context large language models, LLMs, in-context learning, retrieval augmented generation, RAG, and our proposed methods. We begin with long-context LLMs, which are designed to handle extensive context to enhance their generative abilities. Early approaches to increasing context lengths used sparse or low-rank kernels to save memory. Additionally, recurrent and state space models have been suggested as efficient alternatives to transformer models. For causal LLMs, methods like extrapolation and interpolation have effectively increased context window lengths. Recent improvements in attention mechanisms allow LLMs to process input sequences with millions of tokens. Next, we explore in-context learning, ICL, which enhances model performance during inference by using a few task demonstrations. To boost ICL effectiveness, researchers have focused on pre-training strategies that help models learn in context. Selectively using few-shot examples has also been beneficial for downstream tasks. Moreover, reordering in-context examples can further improve performance. With the rise of long-context LLMs, we can now scale the number of examples in ICL, which helps reduce pre-training biases and enhances performance across various tasks. We then turn to Retrieval Augmented Generation, RAG, which enhances language model performance by integrating relevant external knowledge. By optimizing the retrieval process, we can improve context relevance and generation quality. For instance, Replug uses LLMs to guide the learning of a dense retriever model. Encoding documents can also boost knowledge retrieval and generation capabilities. Some methods selectively use knowledge from documents to make LLMs more robust against irrelevant context. For example, RAF trains models with negative documents to enhance generation quality. Despite advancements, the scaling of inference for long-context RAG methods in knowledge-intensive settings is still underexplored. We aim to investigate how variations in inference computation affect RAG performance, focusing on optimizing compute allocation during testing. In our preliminaries, we define effective context length as the total number of input tokens used before the LLM provides a final answer. For methods that call the LLM once, this length is limited by the model's context window. However, for iterative methods, the effective context length can be extended based on the strategy used. We exclude output tokens and retrieval costs from our analysis since LLMs typically generate fewer than 10 tokens in knowledge-intensive tasks, and retrieval is generally less computationally demanding than LLM inference. We introduce our demonstration-based RAG/DRAG method, which utilizes in-context learning to maximize the potential of long-context LLMs by generating answers from an expanded input context. DRAG enhances naive RAG by integrating both documents and in-context examples into the input prompt, allowing the model to answer queries in a single inference request. We use a retrieval model to select the top documents from a large corpus, reversing their order to place the most relevant ones closer to the query. By using instruction-tuned LLMs, we create a prompt template that aligns with the formatting of retrieved documents, inputs, and outputs. To address complex multi-hop queries, we propose iterative demonstration-based RAG, ITER-DRAG. This method breaks down complex queries into simpler subqueries, retrieving additional context for each one to generate intermediate answers. Once all subqueries are resolved, we combine the retrieved context, subqueries, and their answers to form the final answer. We generate in-context examples with subqueries and intermediate answers by prompting LLMs to follow a specific format. Each iteration allows LLMs to produce either a subquery, an intermediate answer, or the final answer, with additional documents retrieved as needed. ITER-DRAG continues until the final answer is generated or a maximum number of iterations is reached. We keep examples with intermediate steps and correct final answers to create in-context demonstrations. During inference, we prepend these examples to the initial documents retrieved for the input query. Each inference request results in a subquery, an intermediate answer, or the final answer, with additional documents retrieved for subqueries to generate intermediate answers. We allow up to 5 iterations of query decomposition before producing the final answer. This iterative approach effectively scales test time computation, summing input tokens from all iterations to calculate the effective context length. By learning to decompose queries and retrieve relevant information, ITER-DRAG helps bridge the compositionality gap and enhances overall RAG performance. Section Summary. In this section, we review advancements in long-context large language models, LLMs, that enhance generative capabilities through efficient context utilization, in-context learning, ICL, strategies, and retrieval augmented generation, RAG, methods. We introduce demonstration-based RAG, DRAG, and iterative DRAG, ITER-DRAG, to improve performance on complex queries by leveraging extensive context and iterative retrieval processes, ultimately aiming to optimize inference computation and enhance knowledge extraction. Section: Fixed Budget Optimal Performance. In this section, we explore how to optimize performance within a fixed budget for inference computation, specifically focusing on a maximum effective context length. We recognize that there are various ways to allocate our computational resources by adjusting inference parameters. For instance, in our DRAG approach, we can modify the number of documents retrieved and the number of in-context examples. In the ITER-DRAG strategy, we also consider the number of iterations for retrieval and generation. We denote all these parameters collectively as theta. For each input query and its corresponding correct answer, we apply the RAG inference strategy, which is influenced by theta. We define the effective input context length as a function of the input query and theta, and we obtain predictions based on this setup. We then calculate a performance metric based on the true answer and our prediction. To understand how RAG performance relates to inference computation, we sample different computation budgets. For each budget, we determine the best average performance achievable by exploring various configurations of theta. Our aim is to clarify the connection between the inference budget and the optimal performance we can achieve within that budget, which we refer to as optimal performance. We examine several factors in our parameter set. 1. The number of documents retrieved from a large source like Wikipedia. 2. The number of in-context examples, each consisting of documents, a query, and its label. And 3. The number of generation iterations. In DRAG, we generate answers directly from the input context, while ITER-DRAG involves multiple retrieval and generation steps, allowing us to expand our effective context length without needing longer context windows. We evaluate the performance of our model, Gemini 1.5 Flash, with context lengths up to 1 million tokens on knowledge-intensive question-answering tasks. To manage computational costs, we sample a limited number of examples from each dataset for evaluation. Our evaluation metrics include exact match, F1 score, and accuracy, which checks if the correct answer is included in our prediction. We set our inference computation budgets at various levels, including 16,000, 32,000, 128,000, 1 million, and 5 million tokens. For the DRAG parameter space, we consider different numbers of documents and in-context examples, while for ITER-DRAG, we also test up to 5 iterations. We compare our methods against several baselines, including zero-shot QA, many-shot QA, and retrieval augmented generation. We report the optimal performance for different inference strategies, identifying the best parameters for each computation budget. Some methods are not applicable for certain budgets due to scaling limitations. For example, zero-shot QA cannot increase its prompt size, and many-shot QA is limited in the number of examples it can use. In contrast, DRAG and ITER-DRAG show consistent performance improvements as we increase the maximum effective context length. Specifically, we find that DRAG and ITER-DRAG outperform the baselines, with DRAG performing best at shorter lengths and ITER-DRAG excelling at longer lengths. These findings suggest that increasing the computation budget is advantageous for RAG performance, with each strategy demonstrating strengths at different scales. Section Summary. In this section, we explore how to optimize inference performance within a fixed computation budget by adjusting parameters like the number of retrieved documents, in-context examples, and iterations in strategies such as DRAG and ITER-DRAG. Our findings indicate that while DRAG performs best at shorter context lengths, ITER-DRAG scales more effectively with longer contexts, demonstrating that increasing the computation budget generally enhances retrieval augmented generation performance. Section: Inference Scaling Laws for RAG. In this section, we analyze how performance changes with different effective context lengths by plotting the performance of all configurations across datasets. We visualize drag and iter drag, highlighting the best performance for various maximum context lengths. The fitting results are shown as gray dashed lines, and we provide more dataset-specific results in another section. We observe that optimal performance consistently improves as the effective context length increases, showing a strong linear relationship, which we refer to as inference scaling laws for RAG. Our key findings include: 1. Optimal performance scales almost linearly with the amount of inference computation, suggesting that we can enhance RAG performance by increasing computation for better predictions. 2. For maximum context lengths above 100,000, iter drag continues to scale effectively by combining retrieval and iterative generation, as seen in our main results. 3. Performance gains start to diminish beyond an effective context length of 1 million tokens, with improvements from 1 million to 5 million being less significant, likely due to challenges in long context modeling. Overall, while gains are smaller past 1 million tokens, optimal RAG performance scales nearly linearly with increased inference computation through drag and iter drag. To further understand the dynamics of drag and iter drag, we conduct a grid search over different combinations of parameters and evaluate performance. The results are shown in heat maps, and we also explore varying numbers of documents and examples. We find that scaling, retrieval, demonstrations, and additional generation steps generally leads to performance improvements, but these gains differ based on effective context length and method. Specifically, we note: 1. Increasing the number of retrieved documents usually results in greater performance gains. 2. Increasing the number of examples is more beneficial for iter drag, as it helps improve query decomposition and knowledge extraction. 3. The saturation point for scaling differs between drag and iter drag, with significant improvements for iter drag when increasing examples, while drag shows little impact. Beyond certain thresholds, further increases in documents or examples yield minimal gains or even declines in performance. 4. For a given maximum context length, the best parameter settings depend on the method, metric, and dataset, making it challenging to model performance accurately. In conclusion, while increasing documents, examples, and iterations can enhance RAG performance, each factor contributes differently, complicating the identification of optimal hyperparameter combinations. Next, we quantify the relationship between performance and the parameters set for long context RAG. We propose a computation allocation model for RAG, which can help guide the selection of parameters based on the maximum effective context length. In our experiments, we consistently observe benefits from inference scaling using drag and iter drag. This, combined with our computation allocation model, allows us to derive a nearly optimal solution for long context RAG under computation constraints. We also discuss additional factors that may affect the scaling of long context RAG. One key factor in enhancing RAG performance is the quality of retrieved documents. We analyze how retrieval impacts accuracy and report results across different document sizes. We find that recall scores improve as the number of documents increases, nearing perfect scores with larger sets. However, while recall improves, we see diminishing returns on ranking metrics, indicating potential distractions in the context. Our findings suggest the need for refining retrieval methods to optimize document relevance, especially for complex queries. We also note that iterative retrieval, as seen in iter drag, enhances recall by using simpler subqueries to gather more context for each answer. In summary, while retrieving more documents can improve recall, it does not guarantee better generation quality if the documents are not effectively ranked or filtered, highlighting the need for adaptive retrieval methods to minimize irrelevant content. Section Summary. In this section, we analyze the performance of RAG models with varying effective context lengths, finding that optimal performance scales nearly linearly with increased inference compute, particularly for ITER DRAG. We also observe that while retrieving more documents enhances recall, it does not always improve generation quality, emphasizing the importance of effective document ranking and retrieval methods. Section: Error Analysis. In this section, we analyze errors in our system, noting that despite overall improvements, some issues remain, especially in tasks requiring complex reasoning. We categorize the common errors into 4 types. 1. Retrieval that is inaccurate or outdated. 2. Reasoning that is incorrect or missing. 3. Hallucinations or unfaithful reasoning. And 4. Evaluation problems or refusal to answer. The first category emphasizes the need to improve our retrieval methods and keep our knowledge base current, particularly for complex questions needing multiple facts. We also find that missing or incorrect reasoning steps lead to errors or incomplete answers. Our experiments show that both retrieval and reasoning improve significantly with our ITER DRAG approach, highlighting the value of combining retrieval and iterative generation for multi-hop queries. Additionally, creating reliable language models and strategies to reduce hallucinations could further boost our retrieval augmented generation (RAG) performance. We also observe that current evaluation metrics fall short in some situations, like with abbreviations, indicating a need for more robust evaluation methods. Regarding long context modeling, we discuss its effect on RAG performance. We find that retrieving more documents generally helps, as shown in our scaling section. However, simply increasing the context length in each generation step doesn't always yield better results. Specifically, we see that DRAG performs best with around 100,000 tokens, while ITER DRAG reaches optimal performance with about 1 million tokens by using multiple generation rounds. Our findings indicate that LLMs struggle to effectively use very long contexts, particularly when faced with many similar documents. We suggest that 1. The model needs to improve its ability to find relevant information from large contexts. And 2. Long context modeling should be refined to enhance learning from multiple lengthy examples.